Today we're moving on in chapter 15 with 15b, which is the locus of points. So we look at functions or expressions to represent some known curves like circles, hyperbolas, ellipses, and straight lines. A bit of definitions. A locus is a set of points described by a geometric condition. So the geometric condition could be a rule or a function, but it can also be just a general equation. Um, two particular representations or geometry we're going to look at. First one will be the circle. So by definition, it's a locus of a point P that moves so that its distance from a fixed point C is constant. C is also the center of the circle, and the constant is what we call the radius. The last one is a straight line. So it's a locus of a point that moves so that it is equidistant from two fixed points Q and R. What's particular about that description is that straight line that will represents the positions of the point P is perpendicular to Q and R, and we'll prove that, or we'll show that through an example. Alright, so what I just mentioned with the circle, C with the respective coordinates is the center of the circle, and that distance from P to C is called the radius. Okay, the coordinates of P are x and y. They will be variable as the point P will move around the locus of that circle. The general equation is if you have the coordinates a, b to be the of the point which is the center, this is the general expression. Just keep in mind here those expressions are factorized in terms of x and y. Hence the technique to, when you have a general expressions, you will have to complete the square respectively on the x and the y variables, and any remaining constants you will move it across to the right hand side, and that value will be your radius squared. With what I mentioned before with a straight line, so when you have Q and R will be fixed points, that straight line that describes the point P is being equidistant from Q and R. We can write this geometrical equation. The distance QP is equal to the distance RP. Geometrical description is P is equidistant from Q and R at all times. So you can see graphically that locus of P, which is the red line, that line is perpendicular to QR. First example, or I'll do one example on example 6. There's a few other examples I skipped. You will have a look on the Cambridge textbook. Example 6. Find the locus of point P whose distance from C of the coordinates, and that's the constant. Okay, so what you do is you write your distance CP equals to 3. You use Pythagoras to express the distance CP in the algebraic form. You square that gives you that that locus representation, and you can read from that that's the center to negative 1 is are the coordinates of the center, and 3 squared will give you the radius of 3. With part B, you have a different equation. It's not in that format of the locus of a circle, So here what you will have to is complete the square on both variables. So you do that respectively for the x and y. Attempt the working out yourself. Any remaining terms, so you have -1, -4, we'll move it across the right hand side. That gives you a +6. And by square root that, you get the radius of √6. Here you have the coordinates of the center, -1, +2, which you have down here. Alright, next example is about, we are looking at a straight line. Find the locus of P that is equidistant to Q and R. So what you do is you express the distance QP and RP using Pythagoras again, or the formula for the distance between 2 points. You have two expressions with a square root. To get rid of the square roots on both sides, you square the whole equation. So each expression will be without a square root. And then a little bit of tedious work. You will have to expand the brackets. As you expand the brackets, the square terms will cancel out. We'll leave out just the linear terms into x and y and the constant terms. You regroup the like terms and you get that, hopefully, that nice linear expressions in terms of x and y. For part B, what you will need to keep in is the gradient. So the gradient of that line is -1/2. So keep that in mind. Then what you do is you look at the line that's going through Q and R. You don't need to get the whole line. All you need is its gradient. So using the formula or the rise over run, you get a gradient of 2. As you do, the product of the two is equal to -1. So the two lines are perpendicular. We can also check that that's additional, but that straight line you got in A will need to cross the midpoint of Q and R. So the midpoint of Q and R is, you find the coordinates of that, which is 2 and 3. As you substitute 2 and 3 into or x equals 2 into the line that describes the locus of P, you find out that the y coordinates is also 3, so it belongs to the line or is on the line. Just something to note as well. And alright, and that's it for today. See you later.